So, we have been discussing the friction. In the last lecture, we learned about the form of drag force in different regimes of Reynolds number. In this lecture, we are going to apply those concepts to solve problems. So, consider a ball is dropped from rest at a height h, so in a viscous liquid. Assume that, so this liquid could be something like air, or a fluid which can be air, or some viscous liquid like glycerine or honey, which are typically used in what is called a Stokes law experiment for measuring the viscosity of liquid in a typical BTech first year lab physics experiment, the undergraduate physics experiment. So, assume that the drag force due to the fluid takes the form Ft is minus alpha v. So, alpha is a constant. So, it is linearly proportional to v, and this minus indicates that the direction is opposite to the direction of the velocity. So, in last lecture we find out, now we know under what condition we expect the drag force to take this particular form. So, the question is, find the velocity and height as a function of time. So, here is the solution of how to do it. So, first let us say we take our coordinate system, and let us say we start at some origin, and let us say the vertical direction is y axis, and this is a one dimensional problem. So, we write down the Newton's law for this problem. So, what are the forces acting on the ball? So, let us say this is mass m. So, then the force that is acting is that its weight mg downwards, and then we have this drag force. Now, the sign, so we are going to use minus here, but the sign can be positive or negative depending on the sign of the velocity. So, v represents the velocity, and then this must be equal to, so this is the total force, and now this is an example where the system is no longer at rest, it is moving, it has some acceleration, and the acceleration must be mass times y double dot, and it is given that the initial condition is given at t equal to 0, the coordinate of the position of the ball was y at h, and it is dropped from rest. So, the y dot, that is the velocity at 0. So, this is the velocity at 0 is 0. Now, this equation is easy to solve, and in fact, this is a differential equation that all of you know how to solve. So, for example, you can write this y double dot as the first derivative of velocity and express everything in terms of velocity, and then you have a separation of variable, and then you can integrate, and the left hand side. So, let us say you are integrating from, so you can separate the velocity and time, and you are integrating from time from t equal to 0 to some time t, and on the right hand side at t equal to 0 the velocity was 0, at some time t later the velocity is v. So, if you integrate you get a log function, and then if you rearrange the term you can solve for the velocity as a function of time, and it turns out to have this particular expression, and it is in the negative direction, which means that the ball is going down, because in our way we have taken the coordinate system, the upward direction is positive. And then once you know the velocity as a function of time, so this velocity is dy dt. So, now again you can integrate once more to compute the position as a function of time, and it is also easy and standard integration. So, just an integration of exponential, and if you now plug in the condition that your t equal to 0 y was h, then the final answer becomes this. Now, this one is somewhat different from, so this answer is different as compared to what you normally expect from just a motion. If you drop a ball and it falls with a constant acceleration, the answer is somewhat different. It now has this a new term. So, when you do this calculation, after you get some answer, and suppose the answer is not given, then you have to ask yourself this question always, Does it make sense? Does the answer make sense? So, of course, you can go and check the answer, but if the answer is not there, so then what to do? So, here is a simple checkpoint that works with this problem, that suppose you ignore the drag force. So, then you know what is the ideal result in that you have all of you done in high school. So, ignore the drag force, what does it mean? When can you ignore the drag force? You can look at this equation of motion. So, there are two forces, one force is a constant and the other force is proportional to velocity. So, ignore the drag force means ignore the drag force compared to the weight of the ball. Now, this is possible when the velocity is small. When is the velocity small? At the initial time or close to the initial time, because the ball is starting from rest. So, when the time was small, then velocity was small, and during that period perhaps you can ignore the drag force. Now, how much time is small? So, note that the answer has a this combination alpha times t, and this is sitting as a power of exponential, which means this alpha times t must be dimensionless. This you can check from here, from the dimension analysis here. So, m times alpha times v has a dimension or must have a dimension of force. So, this the dimension of mv is dimension of alpha times mass times the dimension of velocity, which must be of dimension of force, and hence we see that alpha must have a dimension of inverse t. That means alpha times t is dimensionless. Then you can expand this small time means that times be small such that this product alpha t is very smaller than 1. So, that is a measure of small time. So, then you can expand this exponential in a series, and you can, let us say the e to the power minus x is 1 minus x plus x square by 2 minus and so on so forth. So, this you know this is the Taylor series expansion of e to the power minus x. So, I plug it in here. So, this e to the power minus alpha x is just this term, and I chop this series at the higher and higher term has higher and higher order of alpha t, and if alpha t is a number which is smaller than 1, then those numbers are smaller and smaller. So, I chop this series at the second term, and then if I simplify, I get this answer h minus half gt square, which is your standard answer that you get in absence of any drag force. Then you have confidence in your answer. So, in presence of drag force, you have this is the your position is no longer given by this expression, there is some additional term. The more important part of the effect of drag force is that what happens in the limit of large time. So, again large means we can have this dimensionless parameter alpha t. So, you can say if alpha t is much bigger than 1, then the time is very large. So, in this case we can sort of ignore in the expression for v, we can ignore this exponential dependence, and then we get that our velocity approaches a constant minus g by. So, in this expression if I so this velocity is just first term is a constant and the second term is, so if I drop this term it just becomes a constant, which is a ratio of g over alpha, and this is a constant. So, what does it mean that the velocity is constant, or it but note that this is not exactly constant, because alpha t is exactly 0 when t is actually approaches infinity. So, we say that this goes to constant asymptotically, which means if I plot the time, the velocity, the magnitude of velocity as a function of time. So, it starts from 0 and then gradually increase, but its acceleration goes down, and hence it approaches this limiting case as time tending to infinity. and this value is minus g by alpha. Now, this velocity has a name, it is called the terminal velocity. So, it basically means that so what happens is that if you look at the Newton's law of motion, so there is a constant force and a force which is increasing with velocity, but the rate of increase is slowing down. So, as the difference between these two forces, and because V turns out to be negative, so we know that this is a friction which is opposing the relative motion of the ball through the fluid, which means this force is in the opposite direction, opposite to the gravity. So, then the overall force on the object is much less than the weight of the object itself, and as the velocity increases, it gradually approaches a scenario where the two forces are almost equal or equal to each other. So, they cancel each other. So, then if the total force is 0, that means you expect the ball to move with a constant velocity, and this velocity is called the terminal velocity, which has this particular expression, and this is the reason why we survive after getting hit by a raindrop which is falling from a height of 1 kilometer, because so this is a case where you see that the result of the motion is completely different in presence of drag force and in absence of drag force. And so this is a scenario where in real life situation where you absolutely cannot ignore drag force when analyzing the motion of a projectile such as a raindrop. Now, here I make one more comment before going to the next problem. So, this is the following. So, remember that in earlier we defined different types of mechanics problem, and this particular example belongs to the second situation where we have the total force on the particle on the our system is not 0, and all the forces are given. The initial condition, initial location, position and velocity of the particles are given. So, the equation of motion is given, the initial, these are called initial condition is given, and our goal is to determine the trajectory of the particle. So, this problem fits into that particular situation. So, this introduces this very important concept of terminal velocity. Now, we go through very quickly to another example, which is sort of another example of friction, and in this case this is a solid. We are going back to the dry friction or the friction between two solids, and some of you may have already familiar with this problem, but I find it a very nice problem which illustrates the practical application of friction. So, we all tie a rope around some pole when you are tying or some heavy objects such as a boat. You must have all seen this. So, the question is that why do we tie it around a pole? So, this problem helps to analyze that. So, a rope wraps an angle theta. So, this is a rope and this is a pole or a cylinder, a column. So, something like this, and we are wrapping this rope around this. The question is that what is the effect of this, and pull at one end with so this, remember that when we discuss the review the nature of the tension force in a rope in a few weeks back, there we sort of gave an example that the tension in a rope which we normally assume to be uniform need not be the case always. So, this is a situation where the tension in the rope along the rope which is wrapped around this pole is not uniform because of an external force on the acting on the rope, which is the friction between the pole and the rope. So, there is a coefficient of static friction between the rope and the pole is mu. Then what is the largest force rope can exert on the boat without the rope slipping? So, this is the problem. Now, I sort of show you the analysis here and I will quickly go through it. So, the important point here, so this analysis is pretty standard. So, I am not going to sort of go through it quickly, and it is worked out here. So, but the point is that if you look at the rope as your system, and then there are one part of the rope, slice of rope, which makes an angle d theta, let us say, as your system, then there are three forces. So, the tension force from the surrounding part of the rope plus a contact force, a friction for the contact force of the rope and the pole, which has two components. One is the vertical component and other is the component, tangential component. And because of this external contact force, the frictional force T is non-uniform. So, it depends on the angle theta. The important point is that this tends, so it depends on angle theta, which is kind of intuitively obvious. The more length of the rope is contact with the force and more frictional force. So, you can intuitively expect that it will be more hard to pull at one end. So, the friction will try to prevent the rope from slipping, and that is the whole point why we tie the rope around this pole, to increase the length of the contact of the rope with the pole. But what is important is that this happens in an exponential way. So, this is the important part of result from this calculation, that if we look at one slice and do the force balance, what we get is that the difference of the force. So, this difference in the tension on the two sides, which is the frictional, turns out to be exponential in theta. So, this is the crucial part, and which is why this rope, wrapping this rope around the pole is very effective. So, now I invite you to think a couple of questions, which I am not going to discuss, but it will be fun to think from your part, is that why the ropes that you tie, for example, if I want to tie something, some small objects around, if this is my pole, then I have a small rope. But the ropes that are used to tie boats or launch steamers or ships around in the harbor, in the port, they are very thick. Why are they so thick? What does the thickness does to the rope? Second thing is that we not only wrap the pole, the rope around the pole, we also tie some knot. What does the knot play a role? What is the role of a knot? And third question is, what if the pole breaks? So, I invite you to think about these interesting questions, and in the next week we are going to discuss the new topic. But before that, let us summarize what we have discussed so far. So, we have looked at two kinds of friction. So, we have reviewed in this week, we have reviewed the two kinds of friction and the basic Coulomb's law of friction between two solid surface. And we also consider a case, a friction, a drag force between a solid and liquid, and found its expression in different regimes of Reynolds number. And we took some example, and most importantly we found that that when we consider the projectile motion, the drag force is often very significant. And finally, through different examples, I try to convey the message that in real life there are many practical applications of friction. They are very common and they are very useful, sometimes not, but they are very interesting to study. So, thank you. See you next week.